So now we're on part C of the experiment, and this is dealing with acetic acid solutions. So acetic acid, if you didn't know, the formula for it is CH3COOH. It's a weak acid, which means we talked about before, and it partially dissociates in solution. So it's not like a strong acid or base. It doesn't have a one-way arrow. It's got that equilibrium arrow. But basically, this part of the experiment, we're taking 3 different solutions of different concentrations. So the first one is a 1 molar solution, then it drops down to a 0.1 molar solution, and then drops down even more to a 0.01 molar solution of acetic acid. So basically what we want to do here is we're trying to find the Ka value, the equilibrium constant of that acid. And the way we're going to do that is we're going to just make up these solutions, pour them straight from the bottle into a beaker, and measure their pH values with the electrode again. From those pH values, we're going to use just the formula that we talked about before, and we're going to get our H concentration, our H plus concentration. One thing to note here, if you're wondering how you get this concentration of the deprotonated acetic acid, it's just the same as our H plus concentration. When they dissociate equally in water, so you get equal amounts of each. Basically, we set up our equation like we always do. We got acetic acid plus water breaks up into the deprotonated form, which is our base, and then our acid here, the H3O plus, which I again just call H plus. We throw it into an equilibrium constant expression, so we get products over reactants. We got CH3COO minus times H plus over our acid without being deprotonated. So this is just acetic acid on the bottom. So basically what you do, you got the pH from the pH electrode. We want to find H plus, so all we're going to do is 10 to the minus pH, and we get our H plus, and we know that that is the same value for our CH3COO minus. So we got both of those terms from that equation, and then this value just comes straight off the bottle. So for the solution of 1.0 molar, that's all we're putting in, 1. For 0.1, we just throw that in the bottom. So you get 3 different values. And basically that's your Ka. It's pretty simple, but that's how you solve that one. So yeah.